I'm guessing that some of you are done, but some of you aren't. If you aren't done, take just a few minutes to, maybe a few seconds to finish it up. We'll go over our answers. Get this set up. Okay, there we go. All right, well, let's see how we did. I forgot, let's see. Oh, no one here is in Calc 2, so I will mark this down. I didn't type in Calc 2 grade for their quiz, but I'll mark it down here and I'll do yours as well. So this is DiffyQ. So let's see if everyone gets 100. Let me know. So first things first, with this one, it's written a little bit different than, well, I don't know, is this the way the book has it? Something like this? I don't know. This is a system. It's fine. I just did the derivative of each of these, and then I checked to see if that's what I got when I plugged this stuff into here. So you have 2 times x1, 2 times this, plus 3 times x2, 3 times this. It worked out, at least for x1, and then it worked out for x2 as well. So that made me happy, and I figure, okay, that's a solution. So part A is a yes, that one worked. For part B, it wasn't quite as rosy, sadly, because I did the x1 and I thought, did the derivative of this, and it looked fishy. I didn't think that things were going to work out, so I thought, let's just give it a go here and see what I get when I plug x1 and x2 into the top row. And when I did that, I did not get 2e to the 2t, so that's a no. That's not a solution. No. But this one is at least one of them, so you have one solution, one non-solution there. So that's what we want, though, or we don't want the non-solutions, but we want to find solutions to these things, and so that's our goal. Before we go on, though, every year I do this, so I got to do it again, is the Easter. So the couple of you were in my earlier class and said, are you going to do this again? I said, I don't know, and then I got to do it, so I guess I do. Just briefly, I'll do this a little quicker so that these guys don't have to suffer as much. Back when I was about 25 years ago, pretty early in my career, I had this email from this new faculty member. I think she still works here, if I'm thinking of the right person. Anyway, I've copied this a long time ago, so it's been a while. Hi, I'm a new faculty member, and my husband and I are interested in participating in mission trips over spring break. This year's spring break overlaps Easter break. My husband is a pastor and is unable to miss Easter at his church, and so is spring break always scheduled to overlap Easter break? Now, at first, you might wonder, why did this person email this to me? I mean, I am a mathematician, but also you might wonder about the whole spring break issue. Back in the old days, we had a thing called January term. January term was the entire month of January, and then we started spring semester February 1st or so, and February through mid-May was our spring semester. And so spring break oftentimes would bump into Easter just because of the nature of things. So the reason why this person was emailing me, I think, is that they were confused. There was a person, Reverend Joe Noonan, who was our chaplain back then, and he was actually our chaplain up until, I think, 2019 was when he finally quit. And so you can imagine that people got confused between the two of us. And so I would oftentimes get emails for him asking me to officiate at weddings, and he would get emails for me asking him for help with their math problems. I never officiated any weddings, by the way. So I decided to email her back, despite the fact that I was pretty sure that she didn't intend to send her email to me. Hi, I suspect you meant to email Reverend Joe Noonan. I'm Dr. John Noonan. As a mathematician, I can help you. Short answer is that spring break is always scheduled in the middle of spring semester. Easter moves around based on the phases of the moon. The probability that Easter will be during spring break is approximately 0.25. I thought that's probably what she really wanted to know. It's a 45 or a 25% chance, at least back in the old days. Nowadays, 0%, because well, you'll see. the earliest Easter could be is the 22nd of March, and that's always after our spring break. The long answer, and I actually gave her the big long answer and included all of these equations, but I've condensed them for here, is if you look in Luke, you find this, that Jesus, just before the Last Supper, says, hey, we got to get ready for the Passover. And so he sends the disciples. So obviously, Easter is at Passover. And so we need to know when Passover is. So we look in Leviticus and we find this that describes that the Passover happens at the 15th day of the first month of the year. Well, the first month of the year, January? No. This is the Hebrew calendar. And so we have to look up the Hebrew calendar. And in the Hebrew calendar, the first month of the year, at least for the biblical calendar, is the month of Nisan. And Nisan occurs somewhere in March and April. And it's based on the phases of the moon. So the ancient peoples would start their year around the spring equinox, and they'd start counting months after that. So we want the first month after the spring equinox. That's how that works out. Now, interesting, so here's the sort of a shorter version of the answer. It's the first Sunday after the first full moon after the spring equinox. That's when you can find Easter every year. However, the church, of course, because it's the church, isn't satisfied with something that simple. And so they came up with this much more complicated set of formulas. Now, these formulas, I've modernized them a bit. So you can imagine that back in the early 1000 or 900 AD, things would look a little different than this, but you take the year, you take the remainder after dividing by 19, and then you divide by 4, and then by 7, and then you do all these equations, and this actually works to tell you what day Easter will be on any given year. So you can actually compute the day of Easter using these formulae, but it's always the first Sunday after the first full moon after the spring equinox. So, given that, let's see when it is this year. And here is March 21st or so is the spring equinox. We're looking for the first full moon. And of course, that's because the first month of the calendar begins on the new moon. Here's the new moon, by the way, the end of March. So we keep going. And finally, look, here's a full moon right here on Sunday. And so the first Sunday after the first full moon is the 20th. So that's why we have it on the 20th this year. By the way, you might wonder the distribution of years or distribution of days that Easter is. And interestingly, you can get this off of the census website. I downloaded all this data set has the date for Easter over the years from 1600 to 2100. So that's 5 centuries worth of years, and I graphed them, all of the dates over those 500 years, and you can see that the 22nd is the earliest that Easter could be, just the day after the 21st, and then the latest is the 25th of April. So we're pretty late in the game here on the 20th. It's a pretty late Easter. By the way, if you're waiting for the next time that it's going to be the 25th, it's actually 2038. 2038, we will have Easter on the 25th, the latest it can ever be, and everyone's going to go bonkers. There will probably be news reports where, you know how it is. Anytime something unusual happens, they have to fill the news with something. So they'll talk about how unusual it is that Easter is so late, but it's just because of the phases of the moon. Okay, so that's that. I've done it. Next, we need to deal with eigenvalues, eigenvectors. So I need to give you guys a crash course in linear algebra. And I thought that I wanted to explain all the gory details, and then I realized you don't care. So we won't. We'll leave that for linear algebra class. And we'll just get the mechanics. We'll just get the mechanics down and make sure that you understand. I will mention, so the only thing that if you know linear algebra, I'm going to point out how it is that this is so cool. Hopefully it'll make sense to the linear algebra people. But if you don't worry. Don't worry if you don't know linear algebra. It'll be okay. So here's the idea, is that an equilibrium is going to be a place where the derivative is equal to 0, or where you have a slope of 0. So think of this as, this is places where the slope is 0. And so when we're looking for like an equilibrium, let's see, where is my thing? I'll skip all. I've got a lot of gory details here that you don't care about. Just a minute. Matrix review. Okay, so uh, how about this? I'll just mention this little fact about this equation here. This equation in particular is that you can have a unique solution as long as the determinant is non-zero, the determinant of this matrix. Okay, so those of you who don't know linear algebra, don't worry. But this is where determinants come in, is determinants determine whether or not you have a unique solution to a system of equations or not. If the determinant is zero, it means that there is not unique solution. If it's non-zero, then there is a unique solution. So anyway, let's see, going on here, determinant, here's the determinant, and we're going to be sticking with 2x2 matrices, so this is all you really need to know with this. So the nonlinear algebraists, determinant is this thing, where you're multiplying those two numbers together, multiplying these two numbers together, and you're subtracting the upper diagonal from the lower diagonal. You saw something similar to this in multivariable calculus, where you did this to find the cross product. So it's a very similar procedure, but there's only one diagonal each direction. So that makes things a lot easier. Okay, I want to skip to the stuff that you care about. What is this? Okay, so is this something? No, we don't want that. Yeah, why don't I have a system that I can actually solve? Okay, so here's the way that we're going to do that. In fact, let's take a look at the one that you have on your quiz. That'll be a lot easier to do. Let me just switch back over to the quiz here. That way we can demonstrate using this system. So once you have, let's get a nice blank one there. Yeah, ignore the A and the B down there. It's just this is what I care about. So this, once you have this system of differential equations, we could rewrite this like this. So I'm going to use big capital X to represent this vector, x1, x2. And so the way I would write this is I would write big capital X prime is equal to some matrix, we'll explain in a minute, times big capital X. So big capital X prime is this thing right here. So that is big capital X prime. The matrix, the A matrix, are the coefficients. A is this stuff, 2, 3, 3, 2. And then the big capital X, of course, is just that vector that represents the solutions there. So just some notation. And once again, if you don't know linear algebra, it's okay, because we're going to learn how to deal with this. And it's just going to feel like this thing that you like an algorithm that you're going to do. Hopefully the linear algebraists will say, oh, wow, that's like, now I see why eigenvectors matter. But for maybe most of us, maybe you don't care. You just want to know the mechanics of this. Okay, so the goal is to figure out a solution to that differential equation up there, which represents this system of differential equations. So what I'm going to do to solve this differential equation is I'm going to think about this this idea that what I'm looking for is these equilibria, if you will. So here's the idea is I'm looking for, so here I'll just write this down really quick here, is that I'm seeking, sorry, this sort of a thing. I'll call this V1 and V2 times e to the, what letter do I want to use up here? R. We've used R before, haven't we, for this sort of thing. So it's just so that it feels familiar. I know I mentioned this last time that we're, that back when we were doing second order differential equations, we did something similar to this. And so this is a similar situation to that. Now you'll notice that both of these, take a look at this one. We'll come back to what we're looking for in a minute. This one could be written like this. You have 3 and -3 as the coefficients times e to the -t. So when I write this, these two things, the thing in the box here and this here, they represent the same idea. So there's another linear algebraic thing that you're used to vectors if you're in linear algebra, and that shouldn't be too much of a shock. But if you're not used to that, that's all that means is that you have two solutions. Well, you have the two pieces. The x1 is the top x2 is the bottom, and both of them are multiplied by e to the negative t. So we're looking for things like this. This is a solution, by the way. This one is a solution. We figured that out. It turns out that with a second, two equations with two unknowns, a 2 by 2 matrix, you should have two solutions, just like a second order differential equation has two solutions. So let's see if we can find this particular thing here. So the way we're going to do this is we're going to actually plug this in, very much like I know we've done this, I did this last time. So let's try it out. X prime, so this is going to be x equals this. X prime is r times this vector, whatever it is. Those are numbers. We'll worry about that later. Times e to the rt. So notice what we're trying to figure out. We want to find the situation where this is true. So let's do this. Give me a sec. So x prime r times this vector times e to the rt should equal a 2, 3, 3, 2 times x. What's that vector? Times e to the rt. I ran out of room there, strangely enough. Let me just slide it over a bit. There we go. I keep straying towards the theory or why it works. I know you guys don't care. Sorry, I'll try to, oh, it's not going to move without moving that. Just a minute. I just move the E. There, I got it. Yeah, I'll try. Oh, he made it. He finished. Digital systems, digital camera. Okay, whatever it was. Glad you made it. Okay, so let's cancel the stuff that that is the same on both sides. This thing is the same as that. So what's left is r times the vector is equal to the matrix times the vector. Okay, we're almost there. I know, I guess I'm showing, see, I'm a mathematician. I want to explain where the equation comes from. So it's hard for me just to say, here's the formula. Okay, so we're almost there. So let's just move this all the way to the right, everything to the right, so that you have 0 is equal to the matrix 3, 2 times the vector v1, v2 minus the r times the vector. Okay. I'd like to combine these two and factor out the v1, v2. You might wonder, why didn't I just cancel those to begin with? Well, there's a reason why. It's because linear algebra doesn't let me, but I can combine those two if I'm very careful. So let's do that. 2, 3, 3, 2. Give me a sec here. v1, v2 minus this r0, 0, r. If I rewrite that like that, I know you're thinking that that came out of magic. It's like, it just turns it out that if you multiply this times this, you get the same thing as if you multiply this times this. So r times this is rv1, rv2. This times this, rv1, rv2. It's the same thing. Okay, so we're almost there. So 0 should equal this, 2 minus r. Now I can combine these two matrices. 3, 2 minus r, and then the v1, v2. There it is. Okay. Okay, so here's where we are. We're at this stage, and interestingly, what we want is we want this not to have a unique solution. You see, if this particular matrix equation has a unique solution, I can tell you what that solution is. That solution is 0, 0, which is boring. We don't like 0, 0 for a solution. We want something interesting. So I want this not to be a 0, 0, so I want this to not have a unique solution. And you remember this whole thing about the determinant? The determinant determines whether or not you have a unique solution. So I'm going to do the determinant of this. Bear with me. I will write down the formula in just a minute. So I need to do the determinant of this matrix. So this is an easy matrix to do the determinant of. You can just do the diagonal down, diagonal up. So this will be 2 minus r times 2 minus r minus 9. So you do the down diagonal minus the up diagonal. So that's going to equal r squared, let's see, minus 4r minus 5. Did I get that right? When I did all the simplification? I'll give you a minute, make sure that that makes sense. So just a little bit of algebra. And now, remember what the determinant does. It determines if you have a unique solution. I do not want a unique solution, so I want this to equal 0. So let's set it equal to 0. Set it equal to 0. And then we can factor this. This is going to feel familiar because you did this when you were doing your second order differential equations. And you get r equals 5 and r equals -1. R equals -1, r equals 5. That's part of your solution. By the way, those are called eigenvalues. So those of you who know your linear algebra, these are eigenvalues, but they're super important when you get to differential equations because notice what they represent. They represent the exponent here in your one of your unique solutions. So that r there is going to be part of, it's going to be from the eigenvalue. And check it out, this r equals -1, r equals -1 is right there. See that? R equals -1. All right, we still have to deal with the vector, but not to worry. We've got the eigenvalue. Okay, so here's what we're going to do just to explain how this works. Let's see, maybe I can find a good thing here. Just give me a sec so that we have something that we can work on. Okay, systems, just a minute. I don't want repeated eigenvalues. Hold on a minute. Sorry, I've got a bunch of things I can choose from, but I don't want anything weird, at least not yet. We'll have a systems with, I don't want the special cases yet. There, maybe this one? Hold on a sec. Does this have it? I just need an example that we can work on. It's no good. No good. How about this one? Oh, I found one. Okay, I found one. Here, I'll just write it down up here. So we'll come back. We have to piece together the rest of this, but I want to get the eigenvalue situation under control. So let's try another system. Let me jot this down. So we have y1 prime is equal to 5y1 plus 2y2, and y2 prime is equal to y1 plus 6y2. Okay, so here's the job so far. So here's the algorithm. You want to know what to do if you're not a linear algebraist? Number 1, we're going to make a matrix. So make your matrix, call it A. That's your first step. Number 2 is you're going to find what are called eigenvalues. And I'll help you with this because that's a little bit of a chore, but it's not terrible. So I'll write down the formula here in a minute. Let's get matrix A first. See if you can get matrix A. I will mark you as present, and that way I can pick random people. That's not, oh, I wanted to show you that. Yeah, I'll show you this now. So on our Moodle page, you know where to find all the fun stuff. So yeah, I wanted to show you this because I don't know where the other thing is, but on our Moodle page, there it is. There. So on our Moodle page, go to the summer school, and if you go to week 8 of summer school, that's what I want to do. This is what Austin is going to be doing this weekend. He's going to be going to week 8 of summer school because he's missing next week. And so just wanted to point you in this direction if you wanted to do this too. We have systems of differential equations here. I'm in the barnyard, I don't know why. And then, oh look, is this, I'm in the, that's like, what is it called at the end of Lord of the Rings? Yeah, anyway, yeah, you can figure out, oh, look, I'm in the Caribbean. And then I don't know what's going on there. Okay, so Yeah, you can check it out. But basically, what Austin's going to miss is he's going to miss the repeated eigenvalues, which will be next Wednesday, and the complex eigenvalues, which is the following day, so Friday. So those are the two things. So those are the things that Austin's going to deal with this weekend, I'm sure, before he takes the test next Tuesday. So I wanted to just point that out while I was thinking about it. Let's get back to iPad land. Okay, so go ahead and write down the matrix. Sorry, I just happened to notice that I had that tab open while I get your attendance done. Okay, let's do it. 3043. Wait a minute, everyone's here, so I don't have to do anything? Oh, well. All right, let's randomize. Joshua, you know how to make a matrix, don't you? What's this matrix look like? All right, so you're going to do something like this, 5, 2, 1, and 6. Beautiful. So there's the matrix. Now, here's the deal. With the eigenvalues, technically what you're doing here, I'll do this in purple just for a sec. You're going to do this, A minus lambda I. Ooh, lambda, do we really want to use lambda or can we use R? Do you guys use lambda back in your linear algebra class? Are you okay with lambda? It'll probably be confusing if we don't use lambda. Let's use lambda. Sorry about that, non-linear algebraists. Instead of using R, like I did up here, we're going to use lambda. It's the same. If it bothers you, you can use A minus Ri. Either way you cut it, what I mean by that is you're going to copy your matrix A. So let's see, I'm just going to copy this thing, duplicate it, copy it down here. And then you're going to throw an extra lambda or R into the diagonal. That's all that means. So when you do that, it just means take your original matrix and then stick a minus lambda along the diagonal. That's all. So I know this is super formulaic, but I feel good about it because we know that this is actually means something, unlike when you're doing this in linear algebra when it doesn't mean anything. Which I know that's not entirely true, but this actually has we can solve a differential equation with this. It's so exciting. Okay, now that we've got that, let's do our determinant. So do the determinant. So the eigenvalues, let me make this part A, part B, part C. Do the determinant of this, A minus lambda I. So just to remind you, in case you get chosen, we're going to do the diagonals. That's it. Okay, who gets to do it? You all know it. Here we are. Andrew knows it, don't you? Andrew, how do I do the determinant? You can either tell me the simplified version or the non-simplified. Excellent. So down diagonal is that nasty set of binomials, and then the up diagonal is just 2. So that works out nicely. All right, so let's see what this is. So this is going to be 30, let's see, lambda squared minus 11 lambda plus 30 minus 2. So that's lambda squared minus 11 lambda plus 28. Does that look right? Okay, so we've got that. Letter D, solve. Solve the, solve. Okay, I'll just write it down. Nice. You can do it, factor it, it's not hard. I'm confident in your abilities. What do you think, Mariah? Do you have some factors to this thing? Oh, yeah, I did it backwards. I was thinking what you were saying. I don't know. There it is. Perfect. Lambda minus 4, lambda minus 7, whichever way you do it is still the same. So my lambdas, lambda equals 4 and lambda equals 7. That's it. So those are our eigenvalues. That was step 2. Okay, there's a third step. Third step. So step 3, and then we'll be done for the day. Step 3 is what are called eigenvectors. Oh, I should have asked. Does Dr. Brad call them eigenvalues and eigenvectors, or does he call them, okay, because that's German for characteristic value and characteristic vector. So you could go either way. Some books call it the characteristic. Oh, is that right? Your own, okay, but it's like characteristic of the item. Now I forgot, we have a German speaker here. That's exciting. So eigen means own. Okay, so these are the values for the matrix. It's owned by the matrix. Okay, no, so that, okay, it makes sense for characteristic. So it's not German for characteristic, but it's the same idea. So I've heard it referred to in both ways. So like the English version is usually characteristic value, characteristic. So it's characteristic for, it's a characteristic of the matrix. Oh, I love it. So eigenvalue, eigenvector. So let's get the eigenvectors. How do we get them? Well, the hint is that we're going to be doing where they come from. There it is. Here is the eigenvector right here. And so we need to go back here. There it is, right there. That's how we get the eigenvector. So that, we're going to solve that equation. Now, here's the thing about this solution that we're about to do. You remember what we just did? We did this determinant, and we set the determinant equal to 0 so that we wouldn't have a unique solution. Well, when we go back and we solve for V1 and V2, you're not going to have a unique solution. That's just, that was the goal, because if there was a unique solution, the only solution would be 0. So we're actually, it's going to be frustrating that there's not a unique solution, but we can still solve for these things. Watch I'll do it up here, and then you'll do it at the bottom one. Here's how this works. We're going to take that equation, the one I've got the arrow for up there. Let me draw it in blue over here, and I'm going to do this for each of my eigenvalues. So r equals 5, and then r equals -1. Here you go. We have, for r equals 5, I have 2 minus 5, and then 3, and then 2 minus 5. And then here are the vectors. And I put the 0 here. It's the same equation. So you see what I've got in the box there? I'm just going to rewrite it. So we're just going to do the same thing. We'll do the same thing down below in just a sec. So I need to solve this. Let me see if I can do that. So if I solve this, I get -3, 3, 3, and -3. And then this is V1, V2 is equal to 0. Now, some of you are expert linear algebraists. You know what this is going to turn into, but I need to do this for the non-expert linear algebraists. So what this means is this is shorthand for a system of equations. In particular, the system of equations is -3v1 plus 3v2 should equal 0. And then the bottom equation is 3v1 minus 3v2 equals 0. So notice that that orange matrix, it's just shorthand. It's a condensed version of this. So don't be scared of the matrix. Okay, now let's see if we can solve these for V1 and V2. Like I said, there's no unique solution, and the reason is that these are the same equation. If you solve this equation for V1, you get V1 equals V2. If you solve this equation, you get the same thing, V1 equals V2. Because of that, you get to choose. There's no unique solution, so you get to choose. You can choose whatever you want for V1 and V2, well, within reason. Haven, what would you like V1 to be? V1 is 2, very nice. Haven wants V1 to equal 2. Well, notice what this says. This says that since Haven wants V1 to be 2, V2 also has to be 2. And so my eigenvector for r equals 5 is going to be, at least because of Haven, it's going to be this vector, 2, 2. But you might say, I didn't want V1 to be 2, I wanted V1 to be 3. Well, then your vector would be 3, 3. Totally fine. Maybe you'd want it to be -5, -5. I don't care, as long as the two numbers are the same. That's what matters for this particular value. So for this eigenvalue, here is the solution. the straight line solution for this, I guess we didn't talk about why it's called straight line, don't worry about that right now, is going to be this vector times e to the 5t. So that is a solution. So this would be, oh, that's capital Y. I think we started out with x's, didn't we? Let's go with a capital X. So that would be x1 is 2e to the 5t, and x2 is 2e to the 5t. In fact, anything, you take this times any constant, and you'll get another solution. So if you pick any constant you like, and you'll get another solution to this thing. And that's because this isn't a unique solution. Let's do the same thing down here for r equals, actually for r equals -1, I don't need to do it because we've already got, look at this. For r equals -1, I've already got a solution. It's right here. So there, 3, -3, that's my eigenvector for that eigenvalue. And so for that one, let's see, we have 3, -3 times e to the -t times another constant. Now, of course, these constants can't be the same constant, so we're going to call that one constant 1 down there. And this one will be constant 2. And then if we want every possible solution, let's just add those two together to get a general solution to this different system of differential equations. Let's see if we can do the same thing down here with this. So we need to get eigenvectors. And the way we're going to get the eigenvectors is we go back to this, a minus lambda I times, I'll call this v, and I'm going to solve that. So let's see if we can do this with these two. So you can pick one, lambda equals 4, lambda equals 7. Pick one of those and do this. I'm going to write it down for lambda equals 4. So if you're a, so let's do it this way. If you're a novice, do lambda equals 4. And if you're an expert, do lambda equals 7. If you're not sure if you're one or the other, pick one. Either one works. So I'll get you started, you novices. And we're going to write this down. So here's just for the novices, I'm taking the matrix up there, and I'm rewriting it down here with lambda equals 4. Whoops. Lambda equals 4. Let's see, 2, 1, 6 minus 4. So I'll give you a sec. All right, we got to finish here in just a minute because ASOL says we have to finish early. So, but if you need to leave, I understand. But let's see, Luke, are you a novice or an expert? You're a novice. Okay, so you're doing the 4. Okay, good, good. So tell me the two equations you'd get. So what's 5 minus 4? The 1. And what does that 1 get multiplied by? That one right there, right? So it's going to be 1v1. Whoops. Sorry, v1. And then what about this 2? What do I multiply that by? Very good, v2. And what does that equal? It should equal 0. Very good. And then on the bottom row, you get the same thing, don't you? 1v1 plus 2v2 equals 0. So they're the same equation. So let's just solve one of them. That means v1 is equal to -2v2. And so now we just have to pick a number. Any number will do. Zechariah, do you have a number in your heart that you want to pick? 7. Okay, so he says v2 equals 7. So let's do that. v2 equals 7. Probably most of you would have picked something like v2 is equal to -1 or 1. I don't care. But 7 works. That means v1 is -14. So at least for Zechariah, his vector for this eigenvalue is going to be this. Let's see. This is going to be 7 and -4. Or sorry, the 14 is on top, isn't it? So -14, 7 times e to the 4t. And then let's multiply that times let's put the constant in the front. That would look a lot better, wouldn't it? constant 1. There it is. So there's my first part of the solution. The second part is going to come from the other. What's the other number? 7. Let's see. We need a expert. Lambda equals 7. I'll get it set up, though. Even though you're an expert, I know you know how to do it. Yeah, by the way, all this matrix and vector stuff, it's just a way of compressing all of the equations down so we don't have to write as much. It's not really anything magical. It just looks confusing because you're not used to it. So those of you who are this is new to, it's just a way of trying to write things a little bit more efficiently. That's all. You'll get used to it. Oh yeah, let's pick someone. Hopefully this will be an expert. Rachel P., are you an expert? You are an expert, so you did the 7, right? Okay, so what are the 2 equations you got? All right, beautiful, beautiful. And so you notice that they're basically the same equation. And what equation does that work out to? Yeah, V1 equals V2. So let's find someone who wants to pick a number. Rachel J., what number do you like? 3? Okay, so 3 for V2 and V1. So that means that this is going to be C2 times 3, 3, because they're the same. Whatever you have at the top, you've got to have at the bottom, and this will be e to the 7t. So if we want to write down the general solution to this, what we're going to do is we're going to copy these. Give me a sec. Paste down here, and then copy this one. Duplicate. Here we are. I'm just going to put a plus here. Bear with me for just one more moment so that I can write it like this. So we have negative 14c1 e to the 4t plus 3c2 e to the 7t and 7c1 e to the 4t plus 3c2 e to the 7t. So all I've done there is I've just separated it out so that you can see the 2 solutions. So the top one just comes from taking the top of everything and putting it all together into a single equation, and then the bottom came from the bottom stuff. So the final answer is that this is the x1 solution, this is the x2 solution, and we're all done. So hopefully we'll be able to see what this means in terms of a graph, maybe on Wednesday. But you can also watch those videos and see whatever was going on in my basement 6 years ago or 5 years ago. All right, hope you crushed that exam. Wait, did he just take the exam you're going to take? Digital systems? No? Oh, let me stop the recording, then yeah, go ahead, Asal. Hope it goes well.